So if I put magnesium into concentrated hydrochloric acid, we get a redox reaction occurring in which the magnesium is going to lose its electrons to the H plus ions in the acid, which is going to turn it into hydrogen gas, which is why you see all the bubbles. Now the question is, well, why does that happen? Why does magnesium lose its electrons to the H plus? And the answer to that has to do with the relative activity. So if you take a look at table J, on your reference tables, you can see a list of the relative activities. On the left side, it shows the metals. On the right side, it shows the nonmetals. And if you take a look, you see that Mg is more active than the H2. So that tells you that Mg wants to be oxidized, because that's what metals do, more than the hydrogen plus ions want to be oxidized. So there's going to be a reaction there. Magnesium's like, yo, one of us is going to be oxidized. It's going to be me. I want it more than you. You're going to take these electrons. I'm going to be oxidized. You're going to become reduced, you're going to become hydrogen gas, and, bubble out. Alright, so in this video, I'd like to take that explanation a step further so that you guys can be able to determine if a redox reaction will occur based on the elements' activities, based on that table J. So the question is, well, why do redox reactions occur? And I'm sure you've been wondering, why do these things happen? One way to think about it is like this. Some metals want to be oxidized more than other metals do, right? There's like a scale. Some of them really, 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 really want to be oxidized, and the other ones not so much, like whatever. And the opposite is true for nonmetals. Nonmetals want to be reduced, so some want to be reduced more than other nonmetals. So if we take a look at table J, we can see the list of their activities, right? Remember that metals want to be oxidized, and nonmetals want to be reduced. So for the metals, this is talking about which ones want to be oxidized more so, and for the nonmetals, it's how much these things want to be reduced. Most active metals want to be oxidized. So lithium is the most active of the metals and on this list, and the most active nonmetals want to be reduced. F2 would be the most active nonmetal on that list, right? We're going to pretty much solely focus on the metals with this unit though. All right, so which wants to be oxidized more? Mn or Ti? The way you figure this out is you just find those two things on this chart. I found Mn, I found Ti. Because Ti is higher, and it says over here, most is towards the top, well then Ti wants to be oxidized more than Mn. What about Zn and Mg? Well, here's Zn, and there's Mg. All right, well, Mg is higher up, so it wants to be oxidized more. Au or Cu? So I find Cu right there, and I find Au. All right, well, which one's more active? Which one wants to be oxidized more? Copper, because it's higher up. And then Fe, I'm looking for Fe, I found it, found iron. And then nickel, found it right there. Which one's more active? Well, it's iron. He's higher up, so iron is more active. Which metals won't react with acids? All right, so that is a good question, and you got to remember that acids give you the H+. So if we're looking at the metals list, even though H isn't a metal, it's listed on there for the relative activities. So we know that H2, well, that is for acids, right? That's what we're talking about. So won't react. So that means they got to be less active than hydrogen. So if we take a look, there's three that are less active than hydrogen, right? Cu, Ag, and Au. If you put those metals in acid, they're not going to react with the H+. All right, so how do we use this to predict if a reaction will occur or not? Well, you need to have one neutral atom and one that is oxidized, right? So you're going to have them compete for which one's going to be oxidized. Now it's competition, right? Who wants to be oxidized the most? If the one that wants to be oxidized the most is already oxidized, then there won't be a reaction. There's no reason to react if it's already oxidized. There's nothing to do. But if the one that wants to be oxidized more isn't, then there's going to be a reaction. It's going to react with the other atom. It's going to be like, yo, I should be the one that's oxidized, not you. I want it more, and we're going to react. All right. So if we take a look, here's an example. We got copper ion. So the copper is oxidized, and we got aluminum metal. Will this reaction occur? Well, let's find them. I found copper here, and I found aluminum up here. All right, well, aluminum wants to be oxidized more, but it's not. So it's going to have to do something about that, right? So will this happen? Yeah, aluminum's more active, and it's not oxidized. So will there be a reaction? Heck yeah, aluminum is going to fight copper, essentially, right? So that reaction would occur. So this is the way I look at it, because this is how my mind works, right? And I got copper, and copper's like, hey, aluminum, what's up, man? And he's like, hey, copper, I see that you're oxidized. What's up with that? Huh? Don't you know that I want to be more oxidized than you do? And he goes, yeah, what you gonna do about it, huh? And then aluminum's like, oh, that's it, it's on. We're reacting. Boom! And then reacting. So what's happening is the aluminum wants to be oxidized more, so it is losing its electrons to the copper. It is forcing copper to be reduced because aluminum wants to be oxidized more so. And, this isn't balanced or anything, but aluminum is going to oxidize, become +3, and the copper is going to reduce to be neutral. It's going to take those electrons, become reduced, and they're going to react. All right, well, what about a very similar situation but different? So here we got copper being neutral, and we have aluminum that's oxidized. So again, we find those two elements on our table J. There's aluminum and there's copper. Now, the thing that wants to be oxidized more is aluminum. All right, well, it is already oxidized, right? So there's not going to be a reaction. The thing that wanted to be oxidized the most is already oxidized. And it's kind of like this, right? So we got copper again being neutral, and we got aluminum being kind of a bully again, +3. And again, copper's like, hey, aluminum, what's up, man? And it's like, hey, copper, check it. If one of us is going to be oxidized, it's going to be me. And copper's like, that's cool. You are oxidized, though. So, oh, that's right. Cool. No need to react then, I guess. Idiot. What was that? What was what? Right? So if the thing that's already oxidized is more active, you're not going to get a reaction. There's no reason to react. It's already oxidized. It's not going to oxidize again. It's done. No reaction. So here's an example. So first step, we go out and figure out the charges. Ag by itself is 0. I look up zinc. It's got to be +2. And then over here, Ag becomes +1 and zinc goes to 0. So now I find those two elements. Let's see, Ag is way down here and Zn is up here. So Zn is the one that's more active. So will this reaction occur? Well, if we take a look, Zn is already oxidized. So it's going to be like, yo, Ag, I'm going to be oxidized. And Ag is going to be like, you are oxidized. And it's going to be like, oh, okay then. That's good. We don't got to react to anything then. All right, so will it occur? No. Which is more active? The zinc. It's already oxidized, so it's not going to do anything. Non-metal examples, right? Just a couple to throw in there. Will it occur? Well, we got here is an example of chlorine and fluoride. All right, well, I find chlorine and fluoride right there. The fluorine is more active, so it wants to be reduced, which it already is. So will you get a reaction? No. It's going to be like, yo, chlorine, I'm going to be reduced. And chlorine's like, you are reduced. Oh, well then, no reaction. But the opposite. If I started with fluorine being neutral and chloride being reduced, then fluorine's going to be like, yo, chlorine, what did I tell you about being reduced? It's going to be me. And it's like, all right, do something. And then they're going to react, and that reaction will occur. All right, which of the following reactions will occur spontaneously? Some more examples. Well, here, all right, nickel and lead. I find lead right there, and I find nickel. Nickel has to end up being oxidized. It starts off being oxidized, so it's happy how it is. This isn't going to happen because it's already oxidized. No reason to react. We got copper and sodium. All right, well, sodium's right, and copper's down here. So sodium's the more active, so it wants to be oxidized. It starts off not being oxidized, but ends up being oxidized. So that will happen. It's going to mix with the copper and it's going to be, yo, copper, I'm going to be the one that's oxidized. And the copper's like, whatever, guess we're reacting. And then they react. All right, lithium and zinc. Well, lithium is way up there and zinc is right here. So lithium is the more active one. It starts off neutral all by itself. The zinc is oxidized. Uh-oh. We're going to get a reaction here. Lithium is going to be like, yo, I want to be oxidized more than you, zinc. Wah! Reaction. So reaction would occur here. And I think I got one more example. I have Fe being neutral. So I find Fe. And HCl, well, that's going to be the hydrogen right there. So I'm looking at those two. Iron wants to be one that's oxidized more. It starts off being neutral, whereas the hydrogen is oxidized. Uh-oh. Iron don't like that. We're going to get a reaction here. We sure are. All right, so some practice. Write the symbol in charge of a metal ion that has a greater potential to undergo oxidation than Na. So let's find Na because they're talking about Na. So I find Na, and it wants one that is greater potential to undergo oxidation, so more active. Well, you have a whole list of them. Everything above it would work. Any one of these would work to answer that. All right, next one says write the symbol in charge of a nonmetal that has a greater potential to undergo reduction than chlorine. All right, so we got the chlorine there, and it wants something that is more active, has a greater potential to undergo reduction. Well, reduction is what nonmetals do, so which one's more active than that? Only one thing listed there, F2, because it's higher up. That's more active than chloride. And yeah, so I'm going to skip this part. That's all I got. See you guys in class. Bring questions.